First of all, thank you for the invitation, and I will present the main result of my postdoc I did in Paris. I just changed a little bit the title, and I will talking today about the East African transform margins and the relationship between the plume activity, which is located in the Natal Valley. So first, I would like to use this map that shows the recent work compilation of transform margins made by Lepine and co-workers. And as you can see, the position of the transform margins is mainly based on kinematic reconstruction. This implies that transform margins were relatively posted in comparison with rifted margins. If I show you here at two nice examples, we have, however, some data offshore. This is the case, for instance, of this plateau just there, of the Falkland, where we have some refraction data, but in any case, we study use a different method, but in general, the data are very sparse along the margins and thus do not allow us to understand the evolution of the transform fault zone for time. And in addition, the rifted divergent margins still show and constrain distal margins and breakup edges, which probably does not facilitate the global understanding. So here, the main goal is to better understand the dynamic of the transform fault zones and the interaction with the plume of Karoo, which is just located in this area, and how to use a series of different seismic profile, refraction seismic profile, and I will show you some nice example of three transform systems. The first one is the Devi, the Limpopo, and then the Hagelas. Just before, it's important to recall that the Gondwana is composed of different cratonic masses, which are fused together during several orogenic events. And as a result, different mountain belts form suture zones between all the plates, which have been successively reactivated during the breakup of Gondwana. And there is a consequence about that, is that there is structural inheritance, and structural inheritance play a major role in crustal architectures and development of margins for time. Another point which is interesting here is the location of the two plume, and we'll focus mainly on the Karoo plume, which is located just there. So there is the Mozambique basin here, the Natal Valley, which is located here, and South Africa here, and you can see here the Lebombo and the Mock line here, which is made of basaltic stuff related to the Karoo leap date at around 180 million years. Another point which is interesting in these unconstrained distal margin breakup edges, if we focus, for instance, in the Somali basin just there, or in the Limpopo, there is a difference of edges around 170 or 167 for the oceanic spreading. So we need to constrain this before discuss the interaction between the plume and the geodynamic evolution of the oceanic spreading. So to do that, we use an exhaustive crustal domain map of South and East African margins to understand the geological evolution. And here, this is the main results. So I don't want to go in detail, but just show you that magmatism become more and more important toward the plume, which is located here. We can recognize in this map the different seaward dipping reflector in violet, which is located south on the Natal Valley, also located here close to the Berahai segment and Angoche segment. And when we go further east here in the Somali basin, there is not much magmatism related to the plume activity. So I will start to show you a section just there that's cross-cut the entire Devi ridge. So here, this seismic line illustrates the Devi in the Mozambique basin, and the oceanic basin here is covered by a thin layer of Jurassic, which becomes thicker toward the transform fault just there. There is a clear ridge that's formed the continental ocean transform boundary between the Mozambique basin and the Madagascar margins. And we can see also a nice fracture of volcanic margin just there, and some inversion, some thrust, and some folding within the sediments. Every sediments here are sealed by this major unconformity, which is apsian, which corresponds to the end of the oceanic spreading in the Somali basin. Now we go further south toward the plume just there, and we see the first section, which is again east-west, sorry, so cross-cut the entire section. And here we can see a clear pre-rift continental basement just located here, and just above here wedges, which is made of magmatism and sediments, and we have an age here of two wells, the Funaloro and Ashenge, and the age of this volcanism is similar to the age of Caribou Plume, so around 180 million years. When we go further east, we see here the localization of the transform faults, the Limpopo here, and we go directly toward the oceanic crust, which is quite thick here, with in red here the marks that define the oceanic moat. Now let's go further south, and here we see a difference between north and south here, because the transform fault zones become more and more wider. Toward the south, we again see here the pre-rift. We also see here the sun rift, so just before the transform movement, date around 180 million years. And then there is the escarpment of the transform fault zones. Here, the crust is a bit strange. It's difficult to say if it belongs to the continental or oceanic domain. But when we go, when we go further east here, we can find again the moho, and in between here there is some seaward dipping reflectors showing central transitional sequences. So during the transform movement, you can have some magmatism filling. That's our interpretation. Again, we go further south. We are now located in the Natal Valley, and the western part of the profile exhibit here the rifted basin. When we go further east, we found again this magmatic crust that we call here a transitional domain, and the major transform segment, which is located here, and here in the east here again we can find the oceanic crust. So similar to the previous one, this strange crust, magmatic crust here, become thicker and thicker toward the south, and we can see again some central transitional sequences made of magmatism. Now, if we use another section, so here we see the transform, and now we are focused in the north-south. So the section cross-cut the entire Natal Valley here. So in the northern parts, here is a scientific profile based on seismic reflection and seismic refraction, which has been published in this area. We can find that there is a thick magmatic infilling associated with the dynamic of the plume at 180 million years. And then there is several rifted area with low angle normal fall that control the deposits which are rich in magma again. So we interpret this like seaward dipping reflector, which is typical of volcanic margins. So here again we have a lot of magmatisms and a strong naking with here the onset of the oceanic crust, and according to the refraction profile, this crust is a bit thick, around 9 kilometers. So probably there is a lot of magmatism during the emplacement of the oceanic stuff. Now we go further west, so we are now located along the Agulhas transform fault zone, which is shown here in black, and we have a section northwest southeast, and here the formation is totally different, and you can see that there is again like the David Ridge, just there a big inversion with a lot of thrust. There is also some fold within the sediments, so there is clearly accretional ridge during the activity of the transform. And there is not a lot of magmatism if we compare to the area of the Limpopo.
You're now at 10 minutes.
Yeah, so if we summarize these different information, we see that these three fracture zones share numerous characteristics. The system are characterized by major and strongly localized ocean-continent boundary faults, which is often associated with a set of strike link to oblique slip fault system that accommodates the transform motion. There is a clear corridor of a fault. It's not just alone one fault through time, and we can record it several motion. And the width of the faults associated with the transform faults vary. This is very important in the case of the Limpopo in this area. So we can then propose with this simplified calendar charts that for the Davis system and the Agulhas system, we can say that these translational events may be related to, in the case of the Davis system, to the early stage of the opening of the Indian Ocean between Antarctica and India, so probably before 140 million years, whereas the Agulhas transform fault zones could be related to the opening of the Weddell Sea between Antarctica and South Africa at 130 million years. But what happened in the Limpopo area? Here we just see a transtensional deformation that starts around 150 million years for the activity of the transform system. But we saw just before that there is different faults that start during the rifting main event. So just after the emplacement of the Carolip that start at around 180 million years. And we propose here that this deformation is a consequence of the activity of the plume. So if I show you now these pictures, this is probably what happened at 180 million years. This is our interpretation. You have Africa and Antarctica. In between, there is the Neopatric domain here, so there is probably some structural inheritance. And then you start to focus the activity of the plume just below this area, close to the natal valley. And when we use the different isotopic data, they follow they fall here in this diagram, and that's matched with the idea of the plume, which is located in this area, because the signature, isotopic signature, is the same. That, for instance, the Roy-Van Dyke complex or the Siberia Codfoot basalt. We can then propose a simple sketch to explain the geodynamic evolution for time. So here we are during the Permo-Triassic. There is some previous rifting events because we did some basin where we saw some basin in the seismic line, and then also some basin that outcrop in this area. So probably a first event during the Permo-Triassic, which correspond to widespread event, which is recorded in the entire Africa. And then at around 185, probably until 160, so an activity of 30 million years, you can start to localize the plume in the Natal Valley, so in this area. And this is the equivalent just here with this small sketch between the Beira High segment and the Natal segment just there. And you start to localize here the Limpopo transform fault zone, which then in this figure are localized just there. Then at around 156 million years, you start to connect the both segments, the both oceanic spreading with the Natal segment and the Beira High here. So the transform margins start to become active, which is represented here by this in this cartoon just there, and the deformations start to become strike lip and become more and more important southward with a largest area in this area if we compare to the beginning and the onset of the transform. So here, my main take-home message: the transform fault zone are composed of many segments, and they show a great variability of structures, ranging from ornamental faults and faults, normal to reverse faults, either associated with transtension or transpiration. At large scale, these transform zones are very sensitive to kinematic change and also sensitive to variation, probably associated with the plume dynamics. And it is clear that the interaction with the plume modify the structural pattern of the margins and may locally favor the formation of transtensional structures. Thank you for your attention.
Thank you, Vincent. That was a wonderful talk and amazing visuals. It's amazing to take such complicated tectonics and simplify them into pretty diagrams. Are there any questions? You can raise your hand or put something in the chat. While we're waiting, I'm curious, you showed the seismic sections that you showed are shockingly different, even in fairly close proximity. What is the actual seismic coverage that you had to work with to make those models? Did you have a lot more lines, or did you have to jump between lines?
No, that's depend on the area. In the case of the Davy Ridge, we have a lot of seismic, so we can interpret the things quite correctly. This is similar to the Mozambique basin just there. We are approximately between 5 and 10 seismic line, so it's quite nice, and we can see this variability, which is quite important, because most of the previous study just use 1 or 2 seismic line, and there is a big gap in between these 2 lines. But this is not really the case in the Limpopo and in the Davy case just there.
Excellent. And there's no 3D data, I don't imagine.
Yeah.